Hello everyone, welcome to my second lecture on quantum mechanics. In the first lecture we discusses the properties of and definition of a vector space, and we will continue with the after that first lecture. Today we will mainly talk about inner products. We all are familiar with the definition of dot product. If we have two vectors A and another vector B, then the dot product is defined as AB cos theta, where A is the magnitude of the A vector and B is the magnitude or length of the B vector. Theta is the angle between A and B. And in component form, they have also a form in component. In component form, this is given by ax plus ax bx, ay by, and az bz. So first we want to know why the dot product is necessary. Dot product is necessary because dot product can give us the length and angle of two vectors, right? Right. If we do A dot A, we get ax square plus ay square plus az square. This is by definition of length square of A square. So if we want to know the length of a vector, then it is given by root over A dot A. And if we want to know the angle between two vectors, like cosine theta is given by A dot B divided by AB. So by dot product, by the definition of dot product, we can define length of a vector and angle between two vectors. This is our goal. So we want to extend this definition into general case, right, where our vectors doesn't have length and direction. So first we want to know what are the general properties of dot product, right? So the main features or products of dot products are, let's say one is P dot A. Dot product is symmetric. If we change the order of the vectors, it does not matter, the results are same, it's always give us the same number. And two is A dot A will always be greater than 0 or equal to 0 if equal to 0 if A is 0. 0 if A is 0. This is the property of dot product. And another property is linearity. That means these are the three properties of dot product that we know, and we want to generalize these properties into our normal vector spaces, where our vector does not have length and direction. So this generalization of dot product in higher dimensional vector spaces will be called inner product. Or scalar product. Inner product or scalar product. And from our previous lecture we know we can represent vectors like this. Okay, so the inner product, symbol of inner product will be denoted by this line. So this symbol tells us we are taking dot product or inner product between v vector and w vector, and this will give us a number. This is a number dependent on v and w vector. This number, we have to remember that this number can be complex number. Okay, so now we want to fix some axioms that are dependent on these properties of dot product. So we want to fix some axioms for inner product or scalar product. Axioms of inner product. Axioms of inner product. First one is this. We'll explain the axioms in a minute. Let us write first the axioms. And we say that our inner product will follow these rules, these axioms. We have not yet defined what inner product is, but from physical intuition and from dot products rules, we are saying our inner product will follow these rules. We will explain this now. What are the axioms mean? Okay. The first one ensures that VB is real. Okay, and this sign here is mean complex conjugate. Second one also called just means that this is always positive. And the last one expresses the last axiom, expresses the linearity of the inner product when superposition appear as the second factor. So let's see this. Here we have taken a linear superposition of two vectors. So if this linear superposition is in the second vector in our inner product, then our inner product will follow linearity. Okay, so first one gives us that this must be a real value, and it is second one is telling us that the dot product of inner product of a vector by itself will always be positive, and the last axiom tells us the linearity in our vector space. So we are saying that when linear superposition appears as the second vector, then our axiom says that the inner product follow linear equation. But what if linear superposition appear as the first vector in our inner product? What will then happen? So let's evaluate this. Let's say we have the linear superposition as a first vector in our inner product. So from the first axiom we can write this. This is equal to the complex conjugate of, if we change the order, right? This is for our first axiom. So first line is from the first axiom, and second one is for the third axiom. Okay, and so complex conjugate is on the whole here, so this is also written like this. So we must take complex conjugate form of all the numbers, and again from the first axiom this will give us WV, and this is given ZV. So this is our result. As we can see that this does not follow linear equation but linear property, so we can say antilinear if superposition occurs in first vector. So these are the axioms of inner product. We are saying they will follow this rule. The first one will ensure us that V, inner product of V by itself, will always gives us a real number. That's why we have to take the complex conjugate. And second one show us that V, the inner product of V with itself, will always be positive, and the last one just tells us the linearity if superposition occurs in the second vector. But in the first vector, if the linear superposition occurs in the first vector, they don't follow the linear property. So we will now give a definition, and following from the previous lecture, this will be definition number 7. We are saying a vector space which has a defined inner product is called an inner product space. So we're saying a vector space with an inner product is called an inner product space. This is our definition 7. Other definition number 8. We say two vectors are orthogonal or perpendicular if their inner product is 0. It's like the dot product in our three-dimensional vector cases. We know if two vectors are perpendicular to each other, then their dot product is 0, and we are generalizing this in definition 8, that if two vectors of our vector space, the inner product of the vectors are 0, we will say that they are orthogonal or perpendicular, like the three-dimensional cases of vectors. Definition 9. Definition 9 is we will call this quantity written by this as the norm or length of a vector. So this quantity will be called length of the vector. Again, we are actually extending the idea of our three-dimensional vector. We know that the length of our vector is found by dot product, root over dot product of the vector by itself. So we are calling this the norm or length of the vector. And a normalized vector, that means if we divide the vector by its length, the normalized vector has unit norm. Okay, and then we'll go to definition 8. A set of vectors, all of unit norm, which are pairwise orthogonal, will be called an orthonormal basis. Again, this is also an extension of Cartesian coordinate system in generalized vector space. As we know that our I dot j is 0 and j dot k is 0 in Cartesian coordinate, we call them orthonormal basis. Exactly like this, if our basis vectors are all of unit norm and they are perpendicular to each other, that means the inner product of themselves will give us 0, then the basis will be called an orthonormal basis. So this is our some definition that we use later. So now we want to find out a formula for how to evaluate inner product, right? We have explained what are the axioms we will choose now we want to know how to evaluate one or calculate one inner product. Okay, let's say our v vector is represented by this in any basis system, and our w vector is represented by this in any basis system. Now if we take vw, right, if we take vw, it will give us, by the first axiom, summation of I and j, vi will be conjugated and z will be, this will be like this, right? We know them from the axioms of, so this is our inner product, how to calculate it. And let us choose, we know that all the bases are independent bases, they are linearly independent. In the first lecture we have seen that. And so for easier case, we want to let's say we have this basis are orthonormal basis. That means these two basis vectors are perpendicular to each other and they all have unit length or unit norm, right? So if we take orthonormal basis, if I and j are same, then it will give us 1, and if I and j are different, then it will give us 0. This term and this thing is represented by something called Kronecker delta. It is written like this delta thing, it just del ij is 0 if I and j are not equal, and is 1 if I and j are equal. So this will give us Kronecker delta. So our inner product space will be I summation of I and j vi conjugate omega j del ij. So from the definition of Kronecker delta, we can see only the terms will remain when I and j are equal. So we can, and when I and j are not equal, they will be 0. So we can short write them like this. So this is the formula we are looking for. The inner product, definition of inner product, or how to calculate inner product in generalized vector space. This is our formula. Okay, and we have actually we have made an assumption that, let's say, this ij an orthonormal basis, but the question is, can we do this? Can we do this? What if we don't have orthonormal basis? So we are actually we are making use of a theorem. The theorem is called Gram-Schmidt theorem. Gram-Schmidt theorem. This Gram-Schmidt theorem tells us, given a linear independent basis, we can form linear combinations of the basis vectors to obtain an orthonormal basis. So this is telling us if we have independent basis, we can always form an orthonormal basis by taking linear combination of the basis vectors. So we have actually used this idea to think that our bases are orthonormal bases. So this is the desired form of our inner product space. Inner product formula. Now let's look at let's see what happened in this formula if we do this. So by definition it will give us Vi so we know it will give us square that is always greater than 0 or equal to 0 if only Vi is 0, right? So this is called length or norm squared as per our definition of a vector. This is the definition of a vector, norm square. If we want, we can represent this inner product in matrix form. So how does it look like? If we want, we can actually our kth vector, we can write our kth vectors in column, right? v1 v2 dot 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 dot, we have got vn and it's represented by a column. And if we take another vector w, it can also be written so if we want to represent the inner product, we can write the inner product like this. So this matrix form will help us visualize inner products. Okay, so help us visualize inner product. So this was the foundation of our inner product, what axioms we will choose and what are the definition of inner product, or what will how we will evaluate inner products. Let's talk about more this inner product. Our next topic is dual spaces and the Dirac notation. This is our next topic. So if we focus on the matrix form, we can see we can never get a number from two column by the multiplication of two column vectors. So for representing inner product in matrix form, we need one row vector and one column vector. So Dirac says that column vectors are manifestation of abstract vector v or kth in a basis, right? Column vectors are manifestations of an abstract kate vector, right? Or kate in a basis. So this new thing that we do in the inner product, this thing, we will associate a row vector to an abstract object. This is called bra w. So this form is called kate vector and this form is called bra vector. So if we take adjoint or transpose conjugate of a column vector, we will get a new row vector like this. Our v was v1 v2 dot 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 dot, dot vn. So if we take adjoint of this matrix, we will get this v1 So by taking the adjoint of this column vector, we are getting a new vector space. So in inner product, there are two vector spaces. The first one is the space of kates, and the second one we will call dual space of brass. So we can see inner products are really defined only between brass and kates. This is called the Dirac notation. Okay, and the basis is how does the basis looks like in these spaces? If we take first basis, it will look like this: 1 0 0 dot 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 dot, dot 0. And the corresponding kate vectors, bra vectors, will look like this. If we take the basis number 2, then this basis will look like this: 0 1 0 0 dot 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 dot, dot 0. So this is the matrix notation of our column and row vectors. The column vector space is called dual space, and the column vector is called is kate space, and the row vector space is called brass space. So one is the dual space of another. And now we want to find out how to know what are the components of a vector, right? Components of abstract vector. We write this like this, the vectors in our basis, let's say orthonormal basis, and we want to know these components, right? We want to know this, what are these components. Let's say we want to know the jth component of these vectors. So we will do the inner product with j and j unit vector and v. It will give us this. And if our vector is expressed in orthonormal basis, we know this is give us Kronecker delta. So we know what will it give us? It give us Vj. All the other i's will get a 0, so we will take as Vj. So if we want to know what is the jth component of our kth vector v, we just need to take the inner product with the jth unit vector, or take the dot product, exactly like our three-dimensional case. So just take the dot product. We can call inner product dot product if we want, it doesn't matter, with the jth unit vector, exactly like three-dimensional case. So now we can write like our kth vector v is expressed by this equation, but we can now write vi can be written iv, right? Because we find out how to find the ith component. So summation of I, we can write vi like this. This is also an expression of k vector. If we want to visualize it in matrix form, right? If we want to visualize our kth vector in matrix form, we can actually write this v1 1 0 dot 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 0 plus v2 0 1 0 dot 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 sum vn zero zero dot 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 1. This is the matrix form of our kth vector. So our next topic is adjoint operation. Adjoint operations, our vectors can be written like this. If we take adjoint of this vector, that means transpose and complex conjugate, then this vector will be like this, which will give us VA. So let's talk about notations much. It is customary to write this as our books will sometimes, and corresponding bar vector corresponding bra as AV. So by this notation, if we get a bra, it is actually equal to V bra A conjugate. Since the relation between bras and kets is linear, we can say that if we have an equation among kets such that AV is just linear superposition of this, the ket vectors, if follow a linear superposition, the bra vectors will also follow this linear superposition. Now, so to take the adjoint of an equation involving bras and kets and coefficients, we have to reverse the order of all factors, exchanging the bras and kets and complex conjugating all coefficients. What I am saying, if we have a representation of bra as ket vector, like this, it can be written as the corresponding bra vector will be so again I'm saying, to take the adjoint of an equation involving bras and kets and coefficients, we have to reverse the order of all factors like this. This is here, so the V will go to I and I will come to V, and exchanging the bras and ket and complex conjugate all coefficients, like here these components are in complex form and we will take the complex conjugate form. So to make an equation from bra vector space to ket vector space to bra vector space, we just need to reverse the order of all factors and complex conjugate all coefficients. So we talk about a base Graham-Schmidt theorem, right? Now we will use that. The Graham-Schmidt theorem tells us that if we have an independent basis, we can always make orthonormal bases by linear superposition of those independent bases. So we want to now know what is the procedure of that, how to make this, how to make orthonormal bases from any independent bases. So let's say we have a vector space, linear vector basis, 1, 2, these are the bases of our vector space and they are all linearly independent. So first orthonormal basis will be very easy. We just have to divide our first basis vector by the norm of this vector. This will give us the first orthonormal basis, where I is given by this. We just divide by the norm of the vector. And for the second vector, let me write it first, then I will explain it. Let's find a vector like this. So we are defining this new vector by subtracting this vector from the second basis. So to orthonormal basis, to be orthonormal basis, this and this will be mutually perpendicular to each other. So let us see, if we do the inner product of 1 with this 2 prime vector, does it give us, or does the inner product vanishes, right? Let's check that. So 1, we can write this like this. So this will give us this. This is one inner product by itself, so it is 1. So we'll find this. It will give us 0. So we already know this 2 prime vector is perpendicular to our first orthonormal basis. So if we just divide this 2 prime by its magnitude, we will get our second orthonormal basis. And for the third one, we can define this. You can check for yourself that this new vector is orthonormal to this vector and also orthonormal to the number 1 vector. And if we again divide this vector by its norm, it will give us our third orthonormal basis. So this is the way that we can actually find out orthonormal basis from any independent basis vectors. If you finding it difficult to imagine what is happening, always think about our 2-dimensional or 3-dimensional vectors. Let's do a problem in 2-dimensional vector field, so vector space, so that we can understand this procedure more. So we are doing a problem. Let's say we are given two vectors like this, 2-dimensional vectors like this. We can see these two vectors are linearly independent of each other. So the problem is we have to find an orthonormal basis. We have to find an orthonormal basis. Our first thing we have to do is let's start with A. If we divide A by its length or norm, we'll get our first basis vector. Let us say this is given by A cap. It will be 3i cap plus 4j cap divided by 3 square plus 4 square and 3 by 5 I cap plus 4 by 5 j cap. This is our first orthonormal basis, and by the formula of Graham-Smith theorem, let's take B prime cap. What we have to do, we have to minus from B this thing. So if we calculate this, the dot product will give us 18 minus 18 by 5, and this is this. If we calculate this, we will find out j cap. We will find out this. Now if we divide this vector with its norm, you can do the calculation yourself. We will get 4 by 5 I cap minus 3 by 5 j cap. So by following Gram-Scheme, the procedure of Gram-Scheme theorem, we have got A prime this one and B prime this one. Now we have to look if they are orthonormal. A cap dot B cap will give us 3 by 5 into 4 by 5 minus 4 by 5 into 3 by 5. As you can see, this will give us 0. So here we have found two orthonormal bases. One is A cap and one is B cap. And if you want to do it yourself, the second question will be, can we generate another orthonormal basis? And what will be this? This is for practicing. Do it yourself. The question is, can we generate another orthonormal basis? This means that if this is the only orthonormal basis we can find out by Gram-Scheme theorem, or can we find another one? Do it yourself for your practice. And now let's see another theorem from inner product space, that theorem 4. We have learned about the dimensionality of vector space in the previous lecture. So this is saying the dimensionality of a space equals the maximum number of mutually orthogonal vectors in it. Theorem 4 says if we have n-dimensional vector space, we can only find n number of orthogonal basis vectors in it. Our next topic is very important. First one is called Schwarz inequality. Let me first write this inequality. Schwarz inequality is called, it is also will be a theorem, theorem 5. It's called that inner product, the value of inner product will be always less than the multiplication of individual length of or norm of the vectors. If you want to visualize it, you can always think about the three-dimensional vectors. It's just telling us that the multiplication of individual lengths of the vectors will always be greater than the value of its dot product. This is called Schwarz inequality. Now we will prove this inequality. To prove this, let's take a vector like this. Why are we taking this? Because it will be helpful for us to determine. Now take inner product of this vector by itself, right? So if we want to write, we can write like this. This is for we can write this like this. We have seen this in today's lecture. Now do this individually. Let's do first this one with this one. It will give us V inner product with itself, and then this with this one. It will give us omega V, it will be here, omega square will be here, and V W, right? Not omega, I'm very sorry. And if you remember, the non-linearity of superposition in the first vector tells us that if we take this one with this one, we will find out that this number, this complex number, will be conjugated. This will be square, it's a real value, and this will be this. If you're wondering how we get this, we are getting this from let's say we are getting this from here. If you see, the components of the first vector will be complex conjugated. Okay, and the last one will be this one with this one. So minus minus will be give us 4. This will be omega to the power 4, and the component of this will be conjugated, and we'll get omega by V plus omega W dot product with itself. Now we know this is what? This is Z dot product with itself. We know from the second axiom, this is always greater than 0 or equal to 0 if Z is 0. Right? And this one give is VV minus you can write like this, finally plus this will give us omega square, right? So this omega square and this will cancel out and will get us omega square. So this term and this term will cancel out. We end up with VP minus omega V, sorry, WV, and VW by omega square is greater than 0 or equal to 0. And if we take this in the right side, we'll get this square, right? You can understand this. So we can write omega square as, we can write the VV as V square into omega square greater than omega V omega, right? So if we just take square root, we'll get V omega. In this line we are taking the square root. This is our proof of Schwarz inequality. And the last one, and another theorem 6. This is also very important. We will use it later in this course. Theorem 6 is called triangle inequality. Triangle inequality. It just tells us if we take the norm of the summation of two vectors, it will be always less than the sum of norm or length of the two individual vectors. Again, if you want to visualize it, you can think of our three-dimensional vector. I just, in three-dimensional we saw that if this is a vector, this is another vector, this will be the summation of these two vectors. So by triangle law in geometry, we know this one will always be less than these two, the sum of these two, or equal to, if they are in the same line, then this will be equal. So we also want to now prove this triangle equality. We'll start by this. We can write this like this. Let's take or V plus W square equal to, we can we're just doing this one with this one, this one with this one. Now V plus W square, this will give us V square plus V by W, VW, and from the first axiom and omega into omega will w into w will give us w square. Now we can write, looks, this is a complex number, this is also a complex number, but they are conjugated of itself. If you know, complex numbers are in this form and conjugate numbers are in this form. If we sum these two, the complex part is cancel out, only the real part is there. So we can write 2 real, this is the real value of v into w. Now in this line I will write this v plus w square is less than or equal to v square plus 2 v plus omega square. We have used that real part of any complex number is always less than the total length of the complex number. Not the 2 will be cancelled out. So if we substitute real with this, we can write this like. So finally we can write v plus w square equal to, not equal to, less than v square plus 2vw plus w square. We have also using the Schwarz inequality here. Schwarz inequality tells us this will be always less than this thing. So finally we can write this is just nothing but v plus w square, and now if we take square root, this gives us this. So these two theorems are very important. This is called triangle theorem, and we have proved it for in general vector space, and theorem 6 and theorem 5 was Schwarz inequality. We have proved it for general case. So I will finish my second lecture here. Thank you very much for watching. If you have any questions or if I made any mistake in this video, please tell me.